Hello, Aleks is here, and we're gonna talk about our module 8 today, which is about multi-source data fusion. I know there should be module 7 as well, but since we start a little bit late this time, I decided to move module 8 a little bit earlier and then module 7 a little bit later. So we'll talk about graphs next time, and this time we'll talk about multi-source data fusion, which is anyway very important topic for you to know, because this is something that you need to know early for your final assignment. Why it's so important? Because multi-source data fusion and multi-source is pretty much how everything is organized in social networks nowadays. You cannot notice, you cannot find social networks that operates only one modality or only one data source. We don't have only text or only image. We always have different ways of interacting, and humans in social networks receive a lot of different multimedia data, multimodal content when it comes to social media computing. So every user gets data about responses of their audiences on their posts. They post multimedia content, and they view videos, they post pictures, and then they will interact with this content in various ways. So you of course know this, and of course you also know that we all actual contributors of this, right? We are those who put this data inside the social networks. And another thing is that nowadays we not just using one social network. There's no people who don't use social networks. There's usually about maybe 50 to 40%, 40 to 50% of those who use two social networks and more. And there are many more people who are using really many social networks at the same time, because the social networks serve different purposes. Some are used by us as messengers, let's say Facebook Messenger. Some are used for professional purposes like LinkedIn. Some are used for more casual private communication. And of course, since they have different directions, same people might have a very different type of look and very different type of posts in different social networks. So LinkedIn is more professional. Facebook could be for some communication with friends, some releases, etc. And then let's say Twitter can be something very, very casual and personal for friends updates. So it all describes us comprehensively by adding all these things together, and therefore this multiple social network really contributes a lot to how we look. And also, of course, when it comes to data science, they contribute to how we can receive the data and how much data we have for processing to do the inference by machine learning. So these comprehensive descriptions are not just related to the scale of the data, but it's also about the availability of the source. So you need to have a different views to describe the people. You need to have a different sources to describe the people, and you need to have be able to receive access to different sources. So just a few examples of different sources, different social networks and real media where information can be found about an artist. And there's just one more example. So this example shows that different data modalities, right? We can have textual data representation, we have visual data such as images, we can also have videos talking about the same people. So all this related to the data representation. So now we have a lot of data, and I will tell you in advance that just having a lot of data is usually not enough to do good machine learning applications. Usually we also need to have good way to process this data, to utilize this data for our machine learning tasks. And if we want to use a lot of training data from different sources, we need to predict based on all this data some nice, interesting applications, like interest of the person, where's the person, let's say, want to be a volunteer or not, what's the person occupation, future possible career path, even health, and of course, whether this guy is more like a business person or social service worker. So actually, there's a lot of different applications available, and it can be defined as a machine learning task when you have a lot of data from different social networks, like on the left top corner, and then you have a new sample. It's a lot of data about that new sample, then you want to use the training classifier trained on multiple source fusion to predict one of those interests or career paths or whatever other application. So this is how multi-source social learning is defined. If you go further, you will know that data needs to be fused, right? So the fusion, like combined from different sources, and this part is called data fusion. When you get the knowledge and combine it from different sources, called data fusion. So the relationships, the relatedness between the data source can be split or categorized in multiple ways. It can be complementary data sources or cooperative data sources, or can be also redundant or consistent data sources. So it sometimes can have the same information from two different sources, and this way, if this level of overlap of the information is very high, we maybe don't need one of these data sources called redundant data sources. And you can see that complementary information comes from various sources that represent different parts of the SEM and can be used to obtain more complete global information. So this data complements each other. So this is a complementary fusion. We also can have example of, let's say, sensor networks when we have, let's say, two video cameras from different views, different fields, and then we can get like a 3D view. The modern 360-degree view cameras in cars, they work in this way. They have multiple cameras, and then this get fused to build a 3D picture of our car from a top look. So even though we have camera from the top, but complementary information from other cameras around the car can actually be used to use computer vision to build like a computer game type of look at our car from top or from a side. So this is how it works. This is like complementary fusion. We also have a redundant consistent fusion. So two sources are the same, and they can be fused to enhance the confidence. Yeah. So for example, personality across multiple social networks, right? Different social networks reinforce the same personality of the given user, same age, same gender, and same interests. And you can use that information to increase the confidence that your prediction is correct. And of course, you can also have the cooperative fusion, where information is combined into some new information source. Yeah, so this information source is usually more complex, and if you look into example, can be visual sensor networks. So when you have video and audio get combined, you are getting let's say movie. Or another can be related in the privacy applications, for example, from one part of for one social network, from one source, you know that the guy is going for vacation, and then from another social network, we know that guy have bought a new car. Yeah, these two informations are pretty much bringing different views on this guy. But if they get combined, if you know the same guy, it actually could be a serious security and privacy issue here, and we might recommend this guy to be enhance their privacy practices in social networks, because if somebody just bought expensive property and also the person, let's say, living at home for vacation, then maybe it's a nice time for robbers to go and rob his home. So separately, these two sources are simple and doesn't bring too much meaning, but combined together, they build a new, more complex information. And this more complex information, in fact, can be used for application that was not even possible to be used when it's a separate data pieces. So this is the cooperative data fusion. We can build various frameworks. We can, like, if you talk about the simple frameworks, and please remember this because this is very common, and this might be one of your questions during your defense. What is late fusion? Late fusion is when you train a models based on different sources, S1, S2, S3, and then you fuse and join and do a joint learning. So this is like a late fusion. So because it gets fused late. And if you want to do data fusion, then you can also use so-called early fusion. When you fuse the features, the data sources, you get some unified features, and then you have model in the end, right? Actually, there's a pros and cons of both. Early fusion, early fusion have issues that you might get very high dimensionality of the data, so your machine learning framework might have difficulties to learn fast. And for example, for late fusion, the problem could be that we don't incorporate this information between different data sources. So sometimes we want to utilize this complementary cooperative information to build more complex knowledge, but since model get trained independently, they are not able to utilize this model. So there's no answer which is better, and they can be used for different applications. So early fusion, we extract unimodal features. Like from each modality, we extract the features. And then we integrate different features into a single representation. And then we get a model in the end. Advantages, of course, features integrate from strands, so it's easy to build, and also we can transform the multi-source learning to traditional single-source learning problem, right? Because we can just combine the features, and we can use our traditional machine learning approaches. Challenges, of course, the course of dimensionality, and also how effectively we can learn feature representations and feature interactions. Early fusion is good, for example, for micro, video, or generally visual analysis. And for example, the way it can be done is you take video, you take voice data, you take textual data, then you combine them together into multimodal feature combination, then you can use supervised learning model to do that. So in early fusion, we combine data together. Then we have this kind of enhanced features processing to capture feature interactions, right? So basically, we might use different approaches to do that. Maybe some projection into some latent space or some linear algebra type of approach to receive a transformed, more compact feature space, and then you can use this feature space. Preprocessing can be not just for normalization, but also for learning correlations between features and combining it into more complex features. This could be quite useful approach. Then you train a model, and this model hopefully will be working better. Usually this kind of algorithms are depending on the problem, and they are quite custom tailored to particular problems. But sometimes, of course, you can just combine features directly and then train models based on that. So there's typical applications of this. So for example, you can do cross-domain social recommendation. So this is just one of the architectures proposed here. So you can do see embedding layers. Then you have input layers, so your features embedding layers. And you have pooling layers that pretty much play as a fusion. Then they get into fully connected layers, something like the multi-layer perceptron. Then you have prediction layer in the end. So this is kind of a typical multi-source fusion network. It's pretty simple architecture. But we also can do an explicit way. So when you have the interactions explicitly presented as cross-feature learned by tree-based models, for example, right? You can have, you can learn the features actually, not necessarily just combine them in this way. Or you could also have some linear algebra approaches like PCA to combine features and use your principal components instead of the actual original space to run your machine learning approaches. Yeah, so there's many ways. So they also have late fusion, and fusion is like based off the actual scores of the classifier. So like fusion of the prediction results. So we again extract unimodal features. We separate models that are learned by different features. So the interactions get not captured. And then the scores get combined to yield the final detection score. So this is also common to be known as ensemble learning, because many models come in as ensembles. They learn it based on data separately. Then at the end, we get a better performance. We can design a separate model to focus on individual strengths of different sources. We can weight them. We can learn the actual combination rules based on stacking, for example, right? Or other techniques for machine learning, how to combine this most smartly, just linearly. And we can actually help the models even reinforce each other. For example, we can use like a boosting to reinforce each of the predictions. The challenges, of course, is how to capture the relationship between different sources, how to combine and come up with these coefficients, and also relations can be different type, and it might have some irrelevant relationships, right? So you also need to figure out how to learn and get it from the data that this particular relationship is irrelevant. So for early fusion in semantic microvideo analysis, output of analysis is learn a separate source for each concept. Yeah, so this is just like it's just a recall. So if we do if you so all this done in based on several assumptions that you will see in the screen here, right? So first assumption, of course, is a confidence of source varying according to different specific contexts. So, for example, see two examples, right? So, the job application. LinkedIn might play a leading role, right? So, like let's say, if you want to predict who this guy is going to be, or which job this guy want to apply, which job to recommend, then maybe job related social networks, LinkedIn, or maybe something like Headhunter in Russia could be a relevant source, and therefore we can multiply and we can boost the confidence of that source. Of another example is like for community detection, social networks. Facebook might contribute the most, right? Because Facebook is famous for its groups, communities, and therefore maybe if you want to go for community detection, social networks, you probably want to prioritize the Facebook data sources compared to, let's say, LinkedIn, like in the previous example. So you could learn some multi-source learning problem, and you can transform your original machine learning problems to be multi-source by just doing some very simple linear algebra approaches. So if you take a linear regression function, I mean, most of you are familiar with it. You can actually modify it to combine different data sources inside. And if you don't have the second term, right, the regularization L2 norm term in the second part, you just have a first part of this equation. There will be just like multiple linear regressions run separately. But since you are going to include one more term that combine all of them together, then you're already getting objective function for multi-source learning objective function that you can use for your smart fusion approach. So this is a basic idea, and yeah, this is empirical laws, and then this is the complexity control L2 norm that is usually used as a regularization. So we want to solve the W and also the alpha, right? Alpha is basically the coefficients that helps to combine the different data sources, and W is actual weights that we want to learn through the linear regression. And this is also source confidence. The alpha S is a source confidence for each of the data sources. Just briefly, right, to let you know that how it works. If you want to go more deeper, there's a Malsar framework. You can read about it and just download the code to see how this objective function works in the MATLAB. But you can also read a couple of papers, especially those related to Malsar, to see how exactly this multi-source learning, machine learning works and objective functions. So there is a second assumption: source consistency. We might have different data sources with respect to the same object. Let's say, right, as a state array, and we can have the same object from a different points of view. Yeah, so we want to actually incorporate this consistency inside our learning model, so that we really sure that the presentations are really consistent and they consistently represent our object, so the model can learn more efficiently. And if it's not consistent representation, then in this case probably we don't want to use the data sample to learn, right? So this is a role of consistency. And we can further enhance our objective function to also include the so-called consistency term, right? So basically we won't be discussing how we want to do the optimization for this objective function, because it's like a little bit outside the scope of this course, right? It's not very trivial, but overall you can look that we have the empirical laws the same as in the previous part, but we also have a complexity control as two regularization parameters. It regularizes the complexity of alpha, regularize complexity of W. Basically, we want to learn our weights, and we also want to learn our weights of each of the data sources. But we also have this second source consistency term. Basically, the source consistency term compares different W's and different data representations. So it's XS and XS with a mark, and then every time they see, okay, are these guys actually consistent with each other, consistently represent the object, and if they are, we also want to make sure that so basically what we want to do is, for those X that are not consistent to each other, we want to minimize their W's, and therefore they will not really affect our final result. So this is a source consistency. And of course, we also have source confidence, as it was in the previous part. So this can be solved by alternate optimization strategy, when we optimize one parameter and consider the rest to be constant, and then optimize another one and consider the rest to be constant. But as I say, this is beyond this course. So for most important thing for you here is to know that if you want to do multi-source learning and you want to build machine learning models that are capable of multi-source learning, you probably want to build a more complex objective functions or neural networks that could really account for different parameters. And these parameters could be the complexity control, can be control of the source consistency, and the source confidence. So I will be giving a couple of examples where this can be used after a 10-minute break. So see you in 10 minutes. Okay, so we got a little break, and let's discuss about applications of multi-source learning and how these objective functions can be actually used to enhance the performance of the machine learning models. So, volunteerism tendency prediction. What was the objective of the task? The objective was to figure out whether a guy or girl tend to become a volunteer. And it was tasked to figure this out from the multi-source data from a social network. Why volunteers are important? Volunteers are important because there's many non-for-profit organizations that require people to work for them, but since they don't earn much revenues, and the whole purpose of this organization is to basically some social service, they need volunteers. They need somebody who's willing to work for free, and therefore it wouldn't be a cost for this organization. So detecting volunteers from social network and recommending these volunteers to let's say back to the employee, back to the non-profit organization can be a very useful task. So if you approach this a little bit more formally, you'll see that it's pretty much a binary classification problem, where we want to get information from multiple social networks, and we want to apply the multiple social network learning approach to detect whether the person is tend to be volunteer or not. In case if the person is tend to be volunteer, then we predict him and can be recommended to the organization to be reached out. So this is just a couple of definitions of who are volunteers, and also this is a little bit information or where these volunteers can be found. This is different modalities from social networks that can be used actually to detect volunteers. So you can see that if you use LinkedIn, we can actually see that this guy have some summary page, textual data. We also have the education level, experience level, honors and awards, and organization. And most important for machine learning, what we also have in the right bottom corner, we have a volunteerism participations. So we can see that this guy have volunteer experience in being participating in a certain organization. It's called this was in education field. So well, this is good enough because we have our ground truth to predict, and we have a lot of multimodal data. But the good thing that except for this information, we also know that this guy is also participating on Facebook, where we can get his information about the places where he studied and worked, some content of him, where he went to, I don't know, for the party, some content that he liked to eat, for example, right? So like education, the posts from events and his interests, and the actual volunteering event that he has attended, right? So that's what he was doing, the education. And also we have his profile on Twitter, and we can see what his other interests, and also what is his education level, and also his relationship status, and also like a movie he likes. So look, this is a typical example. We have 3 social networks. We have the same guy. We have different sources describing the same guy differently, in different ways. And one social network he described more professional side, and another social network he described more in terms of his private activities, and also his communication friends and interests in a third social network in Twitter. We also might have a Quora. Inside Quora, we also have the summary, answers, questions, interests of people, and some groups that participate. And you can actually collect this data via one of the approaches. So one way to do it is through the website called about.me, right? And basically, what can be done is you can just look for information from this website. You can see what are his social networks. So it's basically puts all his social networks together in one batch, and then you can use the social networks to collect the data. So basically, this task has been solved already by providing this website. But of course, there's other ways to do it. For example, one way to do map the same person from different social networks is just monitor his, let's say, Twitter timeline and see whether he did any reposts from other social networks inside his Twitter. And therefore, from there, you can also understand and get whether whether this timeline has been also going in parallel, whether this guy have other social networks where he posts. So data completion problem is another problem that you might face inside the multi-source learning problem, and I guess here is one of the crucial pain points. Yeah. So in order to solve this problem, of course, we want to first see into the distribution of the data, right? So you can see that in the Facebook, we have education, work language, gender, hometown, current. We have distribution of how many profiles they will actually fill up this data. On Twitter, we can see different information, let's say name, location, bio, and avatar, but we don't have, let's say, education and work on Twitter, right? On Quora, we have also fields, and then LinkedIn, we have a lot of fields, and all these LinkedIn fields are usually not available on other social networks. So if you have these four data sources, it's actually could be quite difficult for us sometimes to really figure out which information is important, which is not, and also how to combine these data sources together in order to learn the final complete data representation and combine these sources. So this is a challenge as the missing data. There are many techniques can be used. You can use matrix factorization techniques, which is from linear algebra. You can use your k nearest neighbors approach to basically compare records based on the records what you have, and then fill up the remaining records, the empty records, by those from the nearest neighbors where this record is filled up. Many ways. It might look like this, right? So we have these items that are available in some sources and not available in others, and then if you use nearest neighbor, you can compare nearest neighbor and fill up the same information, right? Just like this. Matrix factorization is a little bit more complex approach from the linear algebra. So basically, you have, it's quite often used in recommender systems where you, for example, recommend movies to people. So you can find another matrix M with a mark, and that another matrix will be factorized matrix, right? So basically, that matrix will be equal. So like, let's say we have a matrix M, and then M it's similar to the matrix M mark, and it can be decomposed as two matrices that can be factored one to another, P and Q, right? So it's called matrix factorization. So now if you want to, and this have an objective function, it's also convex optimization problem. So if you can solve this by gradient descent, sorry, by the way, it's not in a global solution, right? So it's it has to be solved iteratively. But if you solve this objective function, then you might be able to fill up the missing values, and you might not want to use your matrix M, but rather you want to use your matrix FM mark as your replacement of your matrix M, and then you can use optimization techniques like gradient descent to optimize this objective function. You can compute the gradients from this objective function, and then you can find the optimal solution of this M mark that can be decomposed into P and Q. Yeah, so then multiplying your matrix into decomposed matrix, you can get this M mark, and then therefore you can get the filled up places in the original matrix that you didn't have in the beginning. There is a redup here, and on the bottom basically is Python implementation. So if you are interested in matrix factorization, how it works, let's see whether it helps you to understand the technique. Of course, one of the biggest disadvantages of matrix factorization is that your matrix, if it's too big, then the computation will be very expensive. So we'll do this. Okay, nearest neighbors, we don't have this problem, but performance-wise, matrix factorization might be much better. So now, if you go back to the original problem, yeah, and we want to address our multi-source learning problem here, right? So we have Twitter, Facebook, LinkedIn. We have different groups of people with blockwise missing data. You can see there's missing. We can actually use matrix factorization as well to not just fill up the data, but also to make sure that the sources, they are consistent between each other, right? So, and it will be already called a regularized matrix factorization. So what is this approach is? And of course, I don't expect you to understand it fully now. You can read the paper in the beginning as a reference, but in a sense, what it's doing? It's basically trying to figure out the missing data from alternating optimization, right? So based on the alternate optimization algorithm that use the grid coordinators and it's trying to solve the problem of matrix factorization, user regularization, and regularization basically marries these different data sources such that they get consistently representing the overall data. So after this, you can project the new latent space. In this latent space, all sources already completed and combined together. So you don't need to worry much, and you can just walk and the machine learning. The whole framework will look like this. All the same user. The guys represent, every user represents different social networks. For some social networks, we have user representation. If we're missing data, we are getting for example, by matrix factorization, and then we apply multi-social learning framework. Right? And of course, we always care how you can seamlessly sew up multiple sources, add multiple sources together, how to combine them, boost the learning performance. Because it's maybe surprising to you, but by combining more data from different data sources, we not always achieve better performance, but sometimes we can achieve a worse performance. So this type of complex or not so complex approaches can be used for many other applications. So the features that could be used, for example, to represent the data could be some demographic characteristics, some features based on the textual content, such as LIWC, contextual topics, user topics, basically the things that we discussed in the NLP chapter of this lecture. But also can be used some behavioral features, behavioral patterns, some egocentric network patterns. LIWC you were familiar with. I think you remember this website, and these features can be used to distinguish different personality traits, or you can just build a distribution among these LIWC features, and therefore you can use it as efficient data representation. So you can also use, and it's about 80 categories, right? This is just examples, right? So this is taken from the LIWC dictionary, so you can see there's it's a psychological process, studying linguistic dimensions, personal concerns, spoken categories, right? So you can see different types. This is LIWC 2007. You can also do topic modeling. You can use latent directly allocation, or in short, it's called LDA. And this generative probabilistic model. So basically, it counts the word counts. It randomly splits them into topics. Then they do Gibbs sampling. Then it sees whether distribution makes sense. So it's completely random. If it starts boiling down into certain topics, it will be iteratively redoing the sampling process and iteratively adjusting which words belong to which topic. So you might end up having topics detected in the end. So you can use LIWC, you can use user topics. You can also use the contextual topics. Okay, user topics is basically one for each user. We extract all text and we figure out the distribution among which the topic get distributed. So let's say topic 1 is this user post for 50% of the time, topic 2 is 23% of the time, and then topic 3 is the remaining, how much left? 27% of the time, right? So that's how it works. It's like a distribution along the user topic. But we can also use the so-called contextual topics. So maybe it's the friend self-description, so it's our context. It's people surrounding us. And that could also help to describe us. You can utilize perplexity, determine dimensions of topic level features and followers. Followees bio. So basically you see who follow you, you get their bio and also detect the topics of your bio. So basically who follow you define who you are, and this is logic. Different posting behavior patterns, emotions, slang words, acronyms, hashtags, URLs, tweets, retweets, etc. In LinkedIn, you also can get a couple of these interesting topics, summary, interest, language, education, etc. So there are many of them. And you can also go for the egocentric network, like user friends and class-specific users, etc. So basically, you can also employ the structure of the social network, not just content features, as I described before, but also the structure of social network. You have this structure. And based on all this information, you can feed up these features as different data sources. And after that, you can further run the analytics, and you can further run the machine learning prediction, use your regularized matrix factorization, KNN, to combine the modalities and run your multi-source learning model in the end. So do you remember before I was talking about the model that can consider the consistency of the topics and also consider the weight and also consider the strengths of each of the data source? So this model can be used to get solved by alternative optimization strategy. And because we don't have missing data anymore, because we already solved this problem by applying matrix factorization or regularized matrix factorization, we can actually get our results. And you can compare different models. And you can see that not just in terms of the actual efficiency, these multi-source learning models can be better, but also in terms of the time, right? So you can see time-wise, this model also one of the fastest, faster than SVM, for example. And this is very important because if it's as fast as regularized regressions and it's much faster than SVM, and at the same time SVM have a lower performance, in this case, it very often makes sense to really use this kind of multi-source learning approaches. If you look into sources, you can also see that actually different sources have different performance. And what is interesting in this table particularly is that combining all data sources together gives you the best performance. But if you look for sources separately, you can see that, for example, such sources as Facebook plus LinkedIn give you a performance of 76%, while each of them separately give you performance of 73 and 74%. So it's not a very strong uplift. And for example, Facebook and LinkedIn give you a better performance than just Twitter alone. So this is another interesting part, right? So just Twitter alone can give you a worse, better performance for predicting volunteerism, even though Twitter doesn't have a volunteerism label, while let's say LinkedIn have this label. That's where we get our ground truth. What that means to us? It means that getting more data is not always helpful, and that multi-source learning has to be really well defined and well constructed, that they utilize the cross-source efficiencies, that they utilize the different aspects of the data in such a way that data helps each other to improve the performance, but doesn't bring performance down. And this is the issue, this is a challenge that we can address in machine learning as well. There was other research done on university ranking. I will just go quickly through it. So they wanted to rank universities based on the social media data. So basically create a benchmark that can be used instead of those public rankings that might be influenced by governments and by some political reasons. So somebody wants to choose university, and there's so many rankings around the US News, or university ranking, academic ranking of universities, some Chinese ranking. So why don't we go collect data from multiple data sources and try to figure out which university is better. So for example, you can see that if you look into the Global University of Engineering, you can see that Tsinghua University is actually better than MIT, right, in terms of the subject score. But Tsinghua is 59 in the world, and while Massachusetts is number 2 in the world. So what kind of these rankings can be interpreted, how they can be used. And you can see, like, for example, at the same time, National University of Singapore is 49 in the global ranking. So it's higher than Tsinghua, but at the same time 92 in terms of the engineering. Is it correct again or not correct? So most of these things are quite often questionable, and university ranking can be used. So you can get different types of features from different sources, student to faculty ratio, just like a features, employment, reputation, citations per faculty, national student ratio, etc. And you can get a score based on all this, a score proposed by researchers here. So previous ranking systems, they are quite big, labor intensive, only focus on top universities, while the small universities get pretty much missed. So for example, like ITMO University, if you go into the overall world rankings, it might fall into 100 or 200, but honestly, everything that goes below 30 or 50 doesn't really get ranked properly. And therefore, we want to have a better ranking to see the actual ranking of universities on a global level holistically, not based on some biased assumptions. So we can do better, and we want to comprehensively and automatically rank the universities. So we can propose a multi-source, multitask learning model to rank universities more efficiently, and we can use many different data sources to do this. Multitask, multi-source learning has been used for many applications, especially when it comes to recommendation performance. You can find this application in a link. So now the key research is how to, again, fuse the multiple types of data sources, especially for proprietary data sources. And this, let's see, maybe this is the screenshot. This problem was again solved by multitask learning. So you might get the objective function that now not talking about sources, but talking about the tasks, where a task is a combination of different modalities and data types that help you to rank and to do the ranking task. And if you read about multitask learning inside Google, you will see again that multitask learning is pretty much extending our traditional machine learning objective functions into incorporating multiple tasks or multiple sources, and then how regularize the sources between each other so that they help each other to improve the final performance. And I guess this is one of the most important moments you want to take away from this model, is that from this particular lecture, is that when you do multi-source learning, it's very not thoughtful when you don't utilize the relationship between data sources. And you also don't figure out what's the difference between these data sources. This is simply because data sources, they are very different. They describe things in different ways. They can be consistent or inconsistent. They can be comprehensive or not. They can be incomplete. The machine learning model really need to be able to handle all this information to do the job efficiently. So this is a very rich area for research, and there are many fusion networks proposed. There are also deep learning networks proposed. For example, Yan Chi, who is assistant for this model, his main research focusing exactly in the multi-source learning. So if you want to learn more about it, just ask him. He is a professional in this area, especially when it comes to deep learning and building deep networks for multi-source learning. We at the same time have tried many models, and many applications can be still proposed. So it's a very good idea for your next cool solution for this module's final project. On my side, this is all, and I pass the word to the tutorial for today. Thank you very much.